There is a machine floating 1,000,000 miles from Earth that can see farther back in time than anything our species has ever built. It does not just look deep into space. It looks into childhood of galaxies, of stars, of light itself. It sees so far that the light entering its mirrors began travelling before Earth had continents, before the sun was born, before our planet even existed. And when we point it at darkness, the darkness disappears. What it finds there should not exist at all, and yet it does. We begin somewhere familiar. Look up at the night sky. To your eyes, it feels ancient and still. The stars seem fixed, distant, decorative. But even the nearest star beyond our sun is more than 4 light years away. The light reaching your retina tonight left that star when you were younger. When you look up, you're already looking into the past. Now stretch that idea. The James Webb Space Telescope does not see 4 years back. It sees billions. It was launched not to orbit Earth like Hubble, but to travel outward past the moon, past the comfortable reach of astronauts until it reached a gravitational balance point called L2, a place where Earth and the Sun hold it in a quiet, delicate tug of war. Nearly 1,000,000 miles away, 4 times farther than the moon. There it unfolded. A gold mirror, 21 feet wide, composed of 18 hexagonal segments, each coated in a layer of gold thinner than a human hair. Gold not for beauty, but because gold reflects infrared light better than almost anything else, and infrared is the key. Because the deeper we look into space, the older the light becomes, and the older the light becomes, the more it stretches. As the universe expands, it stretches light waves travelling through it. Light that once blazed blue and white from newborn stars gets pulled, elongated, reddened. By the time it reaches us, it is no longer visible to human eyes. It has slipped into infrared. Webb was built to catch that stretched light, the faint heat glow of the earlier stars, the afterimage of cosmic dawn. To do that, it had to become colder than anything else we have ever placed in space. Behind its mirrors hangs a sunshield the size of a tennis court, 5 layers of ultra-thin material, each thinner than a human hair, designed to block heat from the sun, Earth, and Moon. On the sun-facing side, temperatures can reach 230 degrees Fahrenheit. On the telescope side, it drops to nearly minus 390 degrees. Colder than Antarctica, colder than Pluto, only a few dozen degrees above absolute zero. Because if Webb itself were warm, it would glow in infrared and blind itself. So we built a machine that lives in darkness, colder than deep space, so that it can see the faint warmth of the first light ever born. And when it opened its eye, it looked at a patch of sky no larger than a grain of sand held at arm's length. A place that appeared empty, black, harmless. We had pointed Hubble at similar darkness before. It revealed thousands of galaxies hiding in that void. It changed our understanding of the universe. Webb looked again. What it saw was not thousands. It saw tens of thousands. Galaxies layered behind galaxies behind galaxies, spirals twisted like cosmic hurricanes, elliptical swarms of ancient stars, collisions frozen mid-impact. Some were so distant their light began travelling toward us more than 13 billion years ago. 13 billion. The universe itself is about 13.8 billion years old. Webb is not just looking far away. It is looking back to when the universe was less than 5% of its current age. Imagine compressing your entire life into a single year. Webb is showing us the first few days after your birth. And those early galaxies are not small, tentative smudges as we once expected. Some are already massive, already structured, already forming stars at astonishing rates. This should not be so easy. Our earlier models imagined a slow cosmic dawn hydrogen cooling, gravity gently gathering matter into the first dim stars, a gradual awakening. But Webb is finding brightness, complexity, structure. It is as if the universe grew up faster than we predicted. And we are watching it happen in reverse. Because every image from Webb is a time machine photograph. The light entering its mirror tonight may have left its source before Earth formed oceans, before our atmosphere stabilized, before the moon settled into orbit. While dinosaurs ruled, while mammals hid, while continents drifted, that light was travelling, crossing expanding space. And now, after billions of years, it ends its journey in a mirror built by primates who only learned to harness electricity a century ago. We're intercepting ancient photons that have been travelling longer than our species has existed. And they carry stories. Webb does not just see galaxies, it analyses the light itself. When starlight passes through gas, certain wavelengths are absorbed, like fingerprints. Hydrogen leaves one pattern, oxygen another, carbon, methane, water vapour all carve their marks into light. Webb spreads that light into spectra rainbows stretched thin and reads the chemistry of distant worlds. It has detected water vapour in the atmospheres of exoplanets hundreds of light years away. It has identified carbon dioxide around worlds that orbit other suns. Planets we cannot see directly, worlds too faint to photograph clearly. Yet their atmospheres betray themselves in faint spectral signatures. We are tasting alien air from across the galaxy. And farther still, Webb has begun to examine galaxies so ancient that their light emerged during what we call the cosmic dark ages. A time before stars, before galaxies shone, when the universe was filled mostly with hydrogen gas, cooling in silence after the Big Bang. Then gravity pulled that gas into the first star's massive, short-lived giants that ignited the cosmos. They burned hot, lived fast, exploded, seeding space with heavier elements carbon, oxygen, iron, the raw materials for planets, for oceans, for life. Webb is beginning to glimpse the afterglow of those first fires. Not directly yet, but close enough that the darkness itself feels thinner. We're standing at the edge of the observable universe, peering into its infancy, watching structure emerge from simplicity. And every time Webb stares into another seemingly empty patch of sky, it reveals abundance, density, history stacked upon history. The black between stars is not empty, it is crowded with time. And we are only beginning to understand how much of it there is. The deeper Webb looks, the less empty the universe becomes. What once appeared as darkness now feels compressed with history, layer upon layer of galaxies suspended at different depths of time. Some are relatively young by cosmic standards, their light only a few billion years old. Others are so distant that their photons began travelling when the universe itself was still learning how to glow. But something else happens when you look that far back. The rules begin to feel unstable, because the early universe was supposed to be simple. After the Big Bang, everything was nearly uniform hot plasma expanding and cooling. No stars, no planets, no structure, just particles spreading outward. Then gravity slow. Patient gravity began gathering matter into clumps. Those clumps became the first stars. The first stars became the first galaxies. Over hundreds of millions of years, complexity emerged. That was the expectation. Webb is quietly suggesting the universe may have moved faster. It has identified galaxies that appear surprisingly massive only a few 100 million years after the Big Bang. Massive enough that they challenge how quickly matter should have been able to gather. Bright enough that they hint at intense star formation happening almost immediately after darkness lifted. Imagine arriving at a construction site expecting to see foundations being poured, and instead finding skyscrapers already standing. We are still verifying, still refining, still testing interpretations, but the possibility itself is electric. Because it means the early universe may have been more efficient, more aggressive, more fertile. Or perhaps we're glimpsing something we do not yet fully understand. And Webb does not blink. It keeps staring. One of its deepest powers is gravitational lensing. Einstein predicted that massive objects bend space itself. If a massive galaxy cluster sits between us and something farther away, Its gravity can bend and magnify the light behind it like a cosmic lens. Webb uses this natural magnification to see even farther. Light from galaxies that would otherwise be too faint is stretched and brightened by intervening clusters. We see arcs, distorted streaks of light curving around foreground galaxies. Those arcs are background galaxies whose light has been bent by gravity over billions of years. It is as if the universe is helping us look at itself. Through these lenses, Webb has detected candidate galaxies whose light began travelling when the universe was less than 300 million years old. 300 million. If the universe were a 24-hour day, that is within the first half hour after midnight. Everything else are sun, earth, dinosaurs. Humans happens in the last seconds before midnight. And yet we're now imaging structures from that first cosmic dawn. There is something deeply unsettling about that scale, because it forces a new perspective. Every civilization in human histories, every empire, every invention, every moment of joy and suffering, all of it occupies a sliver so thin it barely registers against cosmic time. And yet, here we are building machines that can measure it. Webb also looks not just outward, but through dust. Dust is the enemy of visible light telescopes. Clouds of cosmic dust obscure newborn stars, hiding stellar nurseries behind opaque veils. But infrared light passes through dust more easily. Webb can peer into regions where stars are being born right now. In the pillars of creation, those towering columns of gas first made famous by Hubble Webb reveal something different. The visible light image shows sculpted pillars glowing in golden haze. Webb's infrared vision slices through that haze and reveals the young stars forming inside. It is no longer just a beautiful structure. It is an active birthplace. Hundreds of infant stars, some still wrapped in their birth cocoons, glowing softly in infrared heat. We are watching stellar infancy. And not just in our galaxy. Webb has observed protoplanetary disks, rings of dust and gas around young stars where planets are assembling. In some, it has detected water ice, organic molecules, the building blocks of chemistry that, on Earth, led to life. These disks exist hundreds of light years away, and yet their ingredients feel familiar. Hydrogen, oxygen, carbon. The same elements forged in the first stars Webb is studying at the edge of time. The atoms in your body were born in ancient stellar explosions. That is not poetry, it is physics. Carbon in your cells formed in stars billions of years ago. Oxygen you breathe was forged in stellar cores. Iron in your blood was made in supernovae violent enough to outshine entire galaxies. Webb is looking back toward those early furnaces, toward the beginning of the chain that led to you. That chain stretches unbroken across 13.8 billion years. And here is the strange symmetry. The photons Webb captures tonight may have begun their journey before the atoms that make up your body even existed. Light older than your chemistry. Light older than the Milky Way's spiral arms. Light older than the idea of structure itself. And yet it ends in a mirror crafted by hands descended from stardust. We are not outside this story. We are a late chapter in it. Webb's discoveries do not shrink humanity into irrelevance. They place us within a continuity so vast it feels sacred. We are matter that learned to look back. Matter that built a golden eye, cooled it to near absolute zero, and sent it into darkness to answer a question older than language. What was there before us? And with every image, the answer becomes richer, denser, more intricate. The early universe was not a quiet void slowly waking. It may have been a place of violent, rapid growth, stars igniting in clusters, black holes forming quickly, galaxies assembling faster than we predicted. Some early galaxies appear to host surprisingly massive black holes at their centres. Black holes with millions of times the Sun's mass existing when the universe was still in its infancy. How did they grow so quickly? Did they form from direct collapses of massive gas clouds? Did early stars merge and collapse faster than we imagined? Did the first generations of matter behave differently under extreme density? We are not stalled by these questions. We are pulled forward by them, because every answer Webb provides opens new territory. And the deeper we look, the closer we move toward the first moment light was free to travel at all. There is a boundary, an ancient wall of radiation called the cosmic microwave background. It marks the moment, about 380,000 years after the Big Bang, when the universe cooled enough for light to move freely. Beyond that, light cannot show us directly, but Webb is mapping everything just this side of that wall. It is charting the emergence of structure from near uniformity, from simplicity to galaxies, from galaxies to stars, from stars to planets, from planets to observers. And we are only at the beginning of what it can reveal. There is a moment in the early universe when everything changed. For hundreds of thousands of years after the Big Bang, space was opaque, so dense and hot that light could not travel freely. Photons scattered endlessly, trapped in a glowing fog of charged particles. The universe was bright, but blind. Then it cooled. Electrons paired with protons, atoms formed, the fog lifted. Light was released. That ancient light still fills the cosmos today as a faint afterglow, the cosmic microwave background. It is the oldest light we can see directly, a baby picture of the universe at 380,000 years old. Webb does not look beyond that wall, but it walks right up to it. Everything it captures comes from just after the fog cleared, when gravity began sculpting the first structures out of nearly uniform gas. Picture a calm ocean, almost perfectly flat. Now imagine slight ripples, tiny variations in density. Gravity pulls more matter into the slightly denser regions. Those regions grow denser still. Over millions of years, ripples become currents. Currents become whirlpools. Whirlpool centers ignite into stars. That is how galaxies begin. Webb is seeing those whirlpools in their earliest forms. Some of the galaxies it detects are small and irregular clumpy knots of star formation, without the graceful spiral arms we see in the Milky Way. They look chaotic, unfinished, raw. But others appear surprisingly organized. Disk-like shapes, bright cores, defined structure. And this is where the tension builds. Because structure requires time. To build a galaxy as massive as the Milky Way, 100 billion stars, requires cycles of starbirth and death. Accumulation of gas merges with smaller galaxies. It is a slow cosmic choreography. Yet Webb is spotting galaxies that seem heavy, mature, luminous when the universe was only a few 100 million years old. That is equivalent to seeing a forest where you expected seedlings. We are not rewriting physics overnight. Measurements must be confirmed, distances verified, models adjusted. But even the possibility reshapes our sense of pace. The early universe may not have been timid. It may have been explosive with creation. And Webb does something else extraordinary. It listens for chemical signatures across unimaginable distances. When a distant galaxy's light enters Webb's instruments, it is not just photographed, it is dissected. Spread into its component wavelengths like a stretched rainbow. Within that spectrum are dark lines, absorption features where specific elements block specific colors of light. Hydrogen absorbs at one set of wavelengths, oxygen at another, nitrogen, sulfur, neon all leave fingerprints. From billions of light years away, Webb can tell us what those early galaxies are made of. Hydrogen dominates, of course. It was the universe's original fuel. But Webb is already detecting heavier elements in some of these ancient systems, which means stars had already lived and died there. Stars had fused hydrogen into helium, helium into carbon, carbon into oxygen. Massive stars had exploded as supernovae, scattering enriched material into space. That enrichment happened fast. Fast enough that within a few 100 million years, galaxies were no longer pristine, they were chemically evolving. This matters for a simple reason. Life requires complexity. Not just hydrogen and helium, but carbon chains, oxygen chemistry, heavier elements forged in stellar cores. When Webb shows us heavy elements in early galaxies, it reveals how quickly the raw ingredients for complexity spread through the cosmos. The timeline from simplicity to richness may have been shorter than we imagined. And then there are the black holes. At the centres of most galaxies, including our own, sit supermassive black holes. The one in the Milky Way has about 4 million times the mass of the Sun. Some galaxies Webb observes in the early universe appear to host black holes far more massive than expected for their age. How do you grow a million or billion solar mass black hole in such a short time? Black holes grow by feeding accreting gas, merging with other black holes, but even at maximum feeding rates, growth should be limited. Unless the seeds were already large. Perhaps the first stars were enormous, hundreds of times the mass of the Sun, and collapsed directly into substantial black holes. Perhaps dense clouds of primordial gas skipped star formation entirely and collapsed straight into black hole seeds. Or perhaps something about early conditions allowed more efficient growth. Webb is not solving this instantly, but it is narrowing the possibilities. Every spectrum, every faint red-shifted signal, trims away uncertainty and sharpens the outline of what truly happened. And redshift, that stretching of light, is central to everything Webb sees. As the universe expands, space itself stretches. Light travelling through that expanding fabric stretches with it. The farther away a galaxy is, the more its light shifts toward redder wavelengths. Webb measures that shift precisely. From it we calculate distance. From distance we infer age. When Webb identifies a galaxy with extreme redshift, we are seeing light that has been travelling for more than 13 billion years. That photon began its journey when the Milky Way did not yet exist, when the Sun was not even a cloud of gas, when Earth was not a thought in physics. It crossed expanding space for billions of years without interruption. And now it ends in a mirror suspended a million miles from home. There is something almost intimate about that. A single photon born in an ancient galaxy falls onto a gold-coated surface built by human hands. Its journey completes. And in that completion, we expand our map of reality. Webb is not just increasing resolution, it is extending the boundary of the observable universe. With each deeper field, each gravitational lens, each long exposure, we refine our understanding of cosmic dawn, the period when the first stars reionize the universe, stripping electrons from hydrogen and transforming intergalactic space. That era, called the Epoch of reionization, marked the end of cosmic darkness. Webb is now directly sampling galaxies that contributed to that transformation. We are witnessing the universe turning the lights on. And the further it looks, the more the early cosmos feels less like a void and more like a crowded nursery teeming with formation, energy, rapid evolution. The story is not of emptiness. It is of emergence. From nearly uniform plasma to intricate structure in less than 1 billion years. From simple hydrogen to chemically rich galaxies. From gravitational ripples to star factories. And eventually to observers. We are not peering into a dead past. We are watching the opening act of everything that followed. And every image Webb returns stretches our sense of origin just a little closer to the beginning. Stand on a beach at night and look out over the ocean. The horizon feels like a boundary. Beyond it, the world disappears into blackness. Now imagine learning that the horizon is not an edge but a limit set by time. That is what the observable universe truly is. We do not see to an edge of space. We see to an edge of light travel, a boundary defined by how far light has had time to reach us since the beginning. James Webb is pushing that boundary outward not by travelling farther, but by seeing fainter. Because distance in the universe is not measured in miles. It is measured in patience. Light from the earliest galaxies is unimaginably faint by the time it arrives here. It is spread out across expanding space, diluted, stretched into infrared whispers. To catch it, Webb does something deceptively simple. It waits. For hours, for days. It stares at the same tiny patch of sky, collecting photon after photon, stacking them, building an image slowly from almost nothing. Imagine standing in a dark field trying to see a candle flickering thousands of miles away. One glance reveals nothing, but if your eyes could accumulate every photon over hours, eventually a faint glow would emerge. That is what Webb does. It accumulates ancient light. And when enough of those photons gather, the darkness resolves into structure. In its deepest fields, galaxies appear so densely packed that they look like grains of cosmic sand, each one containing billions of stars, each star potentially hosting planets, each planet orbiting in silence around its own sun. The scale becomes almost violent. Our galaxy alone spans about 100,000 light-years and contains perhaps 100 to 400 billion stars. For most of human history, we did not know other galaxies even existed. We thought the Milky Way was the universe. Now Webb reveals that even in a patch of sky the size of a grain of sand at arm's length, there are thousands of galaxies. Extrapolate that across the entire sky. Hundreds of billions of galaxies. Possibly trillions. The number keeps rising as we refine observations. And each galaxy is not static. They collide. Emerge. Tear each other apart. Webb captures galaxies in mid-collision spiral arms stretched into long tidal tails, cores spiraling toward each other, starbursts igniting where gas compresses. These collisions are not rare accidents. They are a primary engine of growth. Our own Milky Way has consumed smaller galaxies in the past. It is on course to collide with Andromeda in about 4 billion years. Webb shows us that such interactions were even more common in the early universe. Galaxies were closer together. Gravity pulled them into frequent mergers. Structure built itself through impact. Creation through collision. And within those merging galaxies, stars form in furious bursts. Gas clouds collapse under gravity, heating until nuclear fusion ignites. A star is born. Fusion releases energy countering gravity, stabilizing the star. For millions or billions of years, the star shines. Then it dies. Small stars fade gently. Massive stars explode as supernovae, blasting heavy elements into space at thousands of kilometers per second. Those elements seed future generations of stars and planets. Webb sees the glow of such starburst regions even in distant galaxies. It detects emission lines from ionized hydrogen, evidence of intense star formation. In some early galaxies, stars were forming at rates dozens of times higher than in the Milky Way today. The early universe was not quiet. It was incandescent. And then there is dust. Dust sounds trivial, like the fine powder on a shelf. Cosmic dust is different. It is made of tiny grains of carbon, silicates, metals, fragments forged in stellar interiors and ejected by dying stars. Dust absorbs and re-emits light. It shapes galaxies. It cools gas clouds, enabling star formation. Webb's infrared sensitivity allows it to trace dust in galaxies across cosmic time. Even relatively early in the universe's history, dust is already present, which means generations of stars had already lived and died. The cycle of creation and destruction began almost immediately after the first stars ignited. There is something relentless about it. Hydrogen collapses into stars. Stars fuse elements. Stars explode. New stars form from enriched remnants. Planets assemble from leftover disks. Chemistry grows more complex. Over billions of years, complexity compounds. Eventually, somewhere on a small rocky planet orbiting an ordinary star in a spiral galaxy, chemistry crosses a threshold. Life. And billions of years after that, life evolves consciousness. Consciousness builds telescopes. And the telescope looks back to the moment the chain began. Webb is not just cataloguing objects. It is mapping ancestry. When it detects oxygen in a galaxy 13 billion light-years away, It is witnessing the early chapters of the chemical story that led to oceans. When it sees carbon in a distant star-forming region, it is observing the raw ingredient of biology emerging long before Earth existed. This is not metaphor. The atoms in your body were forged in stars like the ones Webb studies. Your calcium, your nitrogen, your iron all passed through stellar cores before becoming part of you. Webb is showing us our origin environment. And yet, as far as it sees, it also encounters limits. There is a maximum distance beyond which no telescope can look using light alone. Because before 380,000 years after the Big Bang, the universe was opaque. Webb approaches that wall. It studies galaxies forming just a few 100 million years after the beginning. It measures how quickly those galaxies reionize surrounding hydrogen, how they ended the cosmic dark ages. But beyond that lies a deeper frontier. Not visible light, not infrared, but something even older. Gravitational waves, neutrinos, faint messengers from epochs we cannot yet image directly. Webb stands at the threshold of the visible beginning. It is not the final instrument. It is the current edge. And that edge is breathtaking. Because for the first time, we are not merely theorizing about cosmic dawn. We are seeing its aftermath in detail. Galaxies assembling, black holes growing, chemistry evolving. The horizon is not empty. It is alive with infancy. And every time Webb sends another deep field back to Earth, we feel the boundary of the unknown shift slightly outward. The ocean does not end at the horizon. It simply waits beyond what we can see. And now, for the first time in human history, we are watching that horizon move. There is a strange paradox in all of this. The farther Webb looks, the smaller we feel. And yet the more central we become. Because every distant galaxy, every ancient photon, every stretched spectrum is meaningless without an observer to receive it. For 13 billion years, light travelled in silence. No eyes, no instruments, no minds. Galaxies collided in darkness. Stars exploded unseen. Black holes fed without witness. Then, on one unremarkable planet orbiting a mid-sized star in the outskirts of a spiral galaxy, matter organized itself into something new. Awareness. And that awareness built a mirror in space. Webb is not just a telescope. It is a milestone in consciousness. But its power is not limited to distance. It also sees sideways across our own cosmic neighborhood with a clarity we have never had before. Consider exoplanets. 30 years ago, we did not know if other stars had planets at all. Now we know of thousands. But knowing they exist is not the same as knowing what they are like. Most exoplanets are too distant and too dim to photograph directly. They are lost in the glare of their stars. So we use transits. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching us. That thin ring of atmosphere leaves chemical fingerprints in the light. Webb measures those fingerprints with unprecedented sensitivity. In one case, it observed the exoplanet WASP 96b, a gas giant about 1,100 light-years away. As it transited its star, Webb detected clear signatures of water vapor in its atmosphere. Water. Not on the surface, this world is far too hot, but in its atmosphere. It also observed carbon dioxide in the atmosphere of another exoplanet, WASP 39b. Carbon dioxide is not rare in the universe, but detecting it across hundreds of light-years with such precision is extraordinary. We are not just spotting planets. We are sampling their air. Webb can even detect hazes, clouds, temperature gradients. In some atmospheres, it sees methane. In others, it sees evidence of photochemical reactions driven by stellar radiation. These are not vague hints. They are chemical profiles. Imagine standing on Earth and identifying the composition of a world orbiting a distant star, not by travelling there, but by analysing a few parts per million changes in starlight. That is what Webb is doing. And this is where the narrative tightens. Because among the countless exoplanets, some are rocky. Some orbit within the habitable zones of their stars' regions where liquid water could exist on the surface. Webb has begun studying systems like TRAPPIST-1, a star about 40 light-years away with 7 Earth-sized planets. Several of those planets lie within its habitable zone. Webb is analysing whether they retain atmospheres at all. Because without an atmosphere, a planet cannot regulate temperature or support stable surface water. In some cases, it appears certain planets may have lost thick hydrogen envelopes. In others, observations are still unfolding. This is frontier science. And every new dataset tightens the question: are we alone? Webb is not designed solely to find life, but it is capable of detecting biosignatures, chemical imbalances in an atmosphere that could indicate biological processes. On Earth, oxygen and methane coexist because life continually replenishes them. Without life, they would react and disappear. If Webb were to detect a similar disequilibrium in an exoplanet atmosphere, it would not be proof of life, but it would be a signal too strong to ignore. We are not there yet, but for the first time in history, we have a telescope sensitive enough to realistically search for such signs. The distance between speculation and measurement has narrowed, and yet Webb's gaze does not stop with planets. It peers into our own galaxy with new clarity. At the centre of the Milky Way lies Sagittarius, a star, a supermassive black hole with about 4 million times the mass of the Sun. Black holes themselves emit no light, but material spiralling into them heats up and glows. Webb's infrared instruments can penetrate the dust that obscures our galactic core and observe stars orbiting dangerously close to this gravitational abyss. It studies the environment where gravity bends space so severely that time itself slows. Near a black hole's event horizon, escape velocity exceeds the speed of light. Anything crossing that boundary is gone from our observable universe. And yet, even here, physics holds. Predictable. Measurable. Webb is not staring into chaos. It is observing extreme order. The same gravity that pulls an apple to Earth governs the dance of stars around a black hole. The same nuclear fusion that powers our Sun powered the first stars Webb now observes at the edge of time. There is unity in the scale. From stellar nurseries in dusty nebulae to galaxies forming billions of years ago, to the atmospheres of distant exoplanets, Webb reveals continuity. The universe is not fragmented into unrelated mysteries. It is one evolving system, and we are inside it. The deeper we look, the more that becomes unavoidable. Webb's images are often released in false colour not because they are fake, but because infrared wavelengths are invisible to our eyes. Scientists map them into visible colours to reveal structure and temperature. Brilliant blues, deep reds, glowing gold. The colours are interpretive, but the data beneath them is real. And when we look at those images, we are not just seeing beauty, we are seeing temperature gradients, chemical signatures, radiation fields, stellar populations. Each pixel carries information from across time. And when we share those images, when they spread across screens and classrooms and conversations, they do something subtle. They recalibrate scale. They remind us that our sky is not static, that space is not empty, that the story of the universe did not begin with Earth. Webb is expanding not just our scientific knowledge, but our emotional horizon. Because when you understand even faintly that the light hitting your screen began its journey billions of years ago, something shifts. You're no longer standing at the centre of existence, but you're also no longer isolated within it. You're connected to an unbroken chain stretching from the first stars to the present moment. And Webb is illuminating that chain link by link. And then there is the silence. Webb does not roar through space. It does not blaze like a rocket once it reaches its orbit. It floats. A machine the size of a tennis court, unfolding like a metallic flower, suspended in gravitational balance 1,000,000 miles from home, permanently facing away from the sun, hiding in its own shadow. It exists in quiet, And in that quiet, it listens to the oldest light in existence. There is something unsettling about how fragile it is. Its mirror segments are aligned with nanometer precision tens of thousands of times thinner than a human hair. If they were misaligned by even a fraction of a wavelength of light, the images would blur into uselessness. When Webb first unfolded, engineers on Earth could not touch it. No astronaut would service it like Hubble. It was too far. Every hinge, every motor, every cable. They had to work. And they did. Over 300 single points of potential failure, and one by one, the telescope deployed successfully. We placed our most ambitious eye beyond reach. And it opened. But what it sees is not just ancient galaxies or distant atmospheres. It sees time in layers. When Webb captures a deep field image, you're not looking at a flat sheet of objects. You're looking through depth through billions of years stacked along a single line of sight. Some galaxies in that image may be 1 billion light years away, others 10 billion, others nearly 13. They are not neighbours in space. They are neighbours in perspective. You are seeing a cross-section of cosmic history in one frame. And the further back Webb looks, the stranger the universe becomes. There was a time when there were no planets, no solid surfaces, no chemistry beyond hydrogen and helium. The first stars were different from stars today. They were likely enormous, hundreds of times more massive than our Sun. Made almost entirely of hydrogen and helium, they burned hotter and brighter than most stars we see now. But they lived fast. Within a few million years, they exploded. Those explosions, the first supernovae, seeded the universe with the first heavy elements. Carbon, oxygen, silicon, iron. Before those first stars died, none of those elements existed. The early universe was chemically simple. After their deaths, it began to diversify. Webb is detecting galaxies already enriched with heavier elements less than 1 billion years after the Big Bang. That means the cycle of stellar birth and death began almost immediately. Stars formed, exploded, reformed. In rapid succession. The universe did not waste time. And then there are the structures we never see directly but infer from the way light bends. Dark matter. Webb cannot see dark matter because dark matter does not emit or absorb light. But its gravity shapes galaxies. It influences how galaxies rotate, how clusters hold together, how gravitational lensing arcs appear. When Webb observes distorted arcs of background galaxies around a massive cluster, it is mapping the distribution of invisible mass. We know dark matter outweighs ordinary matter by roughly 5 to 1. Most of the universe's mass is something we cannot see, and yet its presence is undeniable. Without dark matter, galaxies would not have formed as quickly as they did. Gravity alone from visible matter would not have been enough to gather material into early structures so efficiently. Dark matter acted as scaffolding, an invisible framework upon which galaxies assembled. Webb's observations of early galaxies may refine our understanding of that scaffolding. If galaxies appear earlier and more massive than predicted, perhaps dark matter behaved differently in the early universe. Or perhaps our models of baryonic matter, ordinary atoms, need adjustment. Either way, Webb is not just filling in details. It is testing foundations. And then there is expansion itself. The universe is not static, it is stretching. Galaxies are moving away from each other as space expands between them. The farther a galaxy is, the faster it recedes. This is not because galaxies are flying through space like shrapnel. It is because space itself is expanding. Webb measures redshift with extraordinary sensitivity, refining distance estimates and helping constrain the rate of expansion. And here, a tension appears. Measurements of the universe's expansion rate, called the Hubble constant, differ depending on how we measure them. Observations of the early universe suggest one value. Measurements of nearby galaxies suggest a slightly higher value. This discrepancy is small but significant. Webb's precision may help clarify whether this tension is due to measurement error or hints at new physics. Something subtle may be unfolding. Not a collapse of understanding, but a refinement, a sharpening, the kind that only comes when data improves dramatically. And Webb is delivering data unlike anything before it. Its sensitivity allows it to detect objects so faint that they would have been invisible to every previous telescope. It can observe through dust clouds that blocked visible light instruments. It can measure atmospheric chemistry across interstellar distances. It can peer into the earliest chapters of cosmic history. And yet, even with all this power, it does something profoundly human. It slows us down. Webb's most iconic images are not instant snapshots. They are the result of patience. Long exposures to careful calibration, deliberate analysis. In a culture of immediacy, Webb's discoveries unfold methodically. But when the images arrive, when a deep field is released or a new spectrum confirms the presence of water vapor on a distant world, the effect is immediate. Screens fill with galaxies. Classrooms go silent. For a moment, people pause, because it is not just another image. It is a reminder that we live in a universe nearly 14 billion years old, that the atoms in our bodies were forged in ancient stars, that beyond our sky are billions of galaxies, each with billions of suns, and that a species that once painted on cave walls now builds instruments capable of capturing the faint heat of cosmic dawn. Webb looked deeper into space than any telescope in human history. But what it truly did was look deeper into time, into origin, into process, into the long unfolding chain that leads from primordial hydrogen to conscious observers asking where they came from. And the deeper it looks, the more the universe feels less like a backdrop, and more like a story still being written. And just when we think the scale cannot stretch any further, Webb reminds us that distance is only one axis of extremity. There is also temperature. There is gravity. There is time itself behaving differently under pressure. Webb's instruments are tuned to infrared light, which means they are exquisitely sensitive to heat-faint warmth radiating from objects that would otherwise be invisible. In space, heat is information. A newborn star still wrapped in dust glows in infrared long before it becomes visible in optical light. A forming planet radiates residual heat from its assembly. Even cold molecular clouds just tens of degrees above absolute zero emit faint infrared signatures. Webb sees those signatures. In star-forming regions within our galaxy, it detects protostars embedded in cocoons of gas. These are not fully formed stars yet. They are collapsing spheres of hydrogen, heating under gravity, not yet ignited by fusion. We are watching gravity in the act of building suns. Some of these protostars are surrounded by swirling disks, future solar systems in progress. Within those disks, gaps appear, rings form, clumps gather. Those gaps may be planets carving out orbits. Imagine watching our own solar system 4.6 billion years ago before Earth had oceans, before the moon stabilized our tilt, before life began. Webb is doing exactly that, but in systems hundreds of light years away. And inside some of those disks, Webb has detected water ice and organic molecules' complex carbon-based compounds. Not life, but chemistry that could lead to it. The ingredients for biology are not rare exceptions. They appear to be woven into the normal process of star and planet formation. This is not speculation. It is spectral data. And then there are brown dwarfs. Objects too massive to be planets, but too small to sustain stable hydrogen fusion like true stars. Failed stars, sometimes called them. Webb studies their atmospheres, detecting methane, water vapor, cloud layers made of exotic materials like silicates and iron droplets. On these worlds, clouds are not water. They are mineral rain. Temperatures can range from hundreds to thousands of degrees. They blur the boundary between star and planet. The universe does not divide itself cleanly. Categories are human. Reality is continuous. Webb reveals that continuity, And then there are neutron stars, the collapsed remnants of massive stars that exploded as supernovae. A neutron star packs more mass than the Sun into a sphere about 20 kilometers across. 1 teaspoon of the neutron star material would weigh billions of tons on Earth. Gravity there is so intense that atomic structures collapse. Protons and electrons fuse into neutrons. Matter becomes a dense nuclear lattice. Webb is not designed primarily to study neutron stars, but it observes environments shaped by their violent supernova remnants expanding into space, glowing in infrared as shockwaves heat surrounding gas. Those remnants seed galaxies with heavy elements. Gold, uranium, platinum. Much of the gold in your jewellery likely formed during collisions between neutron stars events so energetic they produce gravitational waves rippling across space-time. Webb exists in a new era of astronomy, one where we combine light with gravitational waves, neutrinos, and radio signals. When 2 neutron stars collided in 2017, gravitational wave detectors felt the tremor. Telescopes across the world and in orbit, including infrared instruments, watched the aftermath glow and fade. That event confirmed that heavy elements are forged in such collisions. The universe does not merely create stars. It creates the periodic table through catastrophe. And Webb, with its infrared sensitivity, can track the cooling debris of these events over time. There is something relentless about it. Creation through collapse, structure through violence, order through extremes, and then there is the ultimate extreme black holes. Webb has observed galaxies where supermassive black holes are actively feeding quasars blazing with luminosities that outshine entire galaxies. These are not gentle objects. As matter spirals inward, friction heats it to millions of degrees. The accretion disk radiates across the electromagnetic spectrum. Jets of particles launch at near-light speed, extending thousands of light-years into space. Some of the most distant quasars Webb observes existed when the universe was less than 1 billion years old, which means supermassive black holes formed astonishingly early. They are not late additions. They are foundational. In many galaxies, black hole growth and galaxy growth appear intertwined. As galaxies form stars, their central black holes feed. Energy from those black holes can regulate star formation heating gas, preventing runaway collapse. It is a feedback loop. Gravity gathers matter. Matter forms stars. Stars die and enrich space. Black holes grow and influence galaxies. Galaxies merge and reshape the cosmos. Webb is tracing these loops backward in time, mapping not just isolated events but relationships. And as we follow these relationships, something profound becomes clear. The universe is not a static sculpture. It is a dynamic process. From quantum fluctuations in the earliest moments after the Big Bang to galaxy clusters spanning millions of light-years, everything evolves. Even now, galaxies are drifting apart as expansion accelerates, driven by dark energy, the mysterious force causing cosmic expansion to speed up. Webb contributes to refining measurements of that acceleration by observing distant supernovae and galaxies. The farther back we look, the clearer the expansion history becomes. And here is the sobering truth. One day, far in the future, galaxies beyond our local group will recede so quickly that their light will never reach us. The night sky will grow emptier. Future civilizations, if any exist, may not see evidence of other galaxies at all. They may conclude their galaxy is the entire universe. We live in a rare era, an era when the expansion has not yet erased the cosmic horizon, an era when light from the early universe is still arriving. And Webb is capturing it while it can. This is not just a telescope looking deeper than any before it. It is a time-sensitive instrument, a witness positioned at a precise moment in cosmic history when the universe is old enough to have structure, but young enough that its earliest light is still visible. We are beneficiaries of timing, matter that emerged late enough to reflect, but early enough to still see the beginning. There is something almost unbearable about that timing. For billions of years, the universe expanded in darkness and fire, stars igniting and dying without witness. For billions more, galaxies matured, spiral arms formed, black holes settled into their gravitational thrones. And only now, only in this narrow slice of cosmic history, has matter arranged itself into beings capable of looking back far enough to see the beginning. We are not at the centre of space, but we may be near the centre of visibility, because the observable universe is not just limited by distance, it is limited by time and expansion. The farther galaxies recede, the more their light stretches, weakens, and eventually fades beyond detectability. Webb is operating in a golden window, and it is using every second of it. One of its most profound capabilities is something that sounds technical, but changes everything's sensitivity to faint flux. Flux is simply the amount of light received per unit area. The earliest galaxies emit almost nothing by the time their light reaches us, not because they were dim, but because distance dilutes. Light spreads out spherically, double the distance, and brightness falls by a factor of 4. Multiply that across billions of light years, and what arrives is nearly imperceptible. Webb's 6.5-meter mirror collects more light than any previous space telescope. Its instruments are designed to detect minuscule variations, tiny differences in intensity that reveal entire galaxies. This is not just improvement. It is threshold crossing. There is a point at which sensitivity becomes transformative. Below it, early galaxies are invisible. Above it, they emerge in numbers that shift models. Webb crossed that threshold, and once it did, the early universe did not look sparse. It looked crowded. Galaxies appear earlier, brighter, more structured than many predicted. Some candidate galaxies show stellar masses comparable to the Milky Way at epochs when the universe was only a few % of its current age. That does not mean our understanding collapses. It means we refine. Perhaps star formation was more efficient. Perhaps gas cooled faster. Perhaps dark matter halos formed earlier and deeper than expected. Or perhaps feedback mechanisms behaved differently in primordial conditions. Webb does not shout answers. It accumulates evidence, and the evidence is reshaping timelines. But Webb is not only looking outward in vast arcs. It is also capable of focusing sharply on single systems with surgical precision. Take planetary nebulae, glowing shells of gas expelled by dying stars like our Sun. When a Sun-like star exhausts its hydrogen and helium fuel, it sheds its outer layers. The core remains as a white dwarf, a dense remnant about the size of Earth. The expelled gas forms intricate patterns, rings, arcs, filaments. Webb's infrared imaging reveals structures within those nebulae that were previously obscured by dust. Layers upon layers of material, ejected in pulses over thousands of years. It shows us the future of our own Sun. In about 5 billion years, the Sun will swell into a red giant, engulfing Mercury and Venus, possibly Earth. It will shed its outer layers, leaving behind a white dwarf slowly cooling for trillions of years. Webb is showing us that destiny in exquisite detail around other stars. It turns abstraction into imagery. And then there are massive star-forming regions like the Tarantula Nebula in the Large Magellanic Cloud. This is not a gentle cloud. It is one of the most active star-forming regions in our local group of galaxies. Webb's view reveals tens of thousands of young stars carving cavities into gas with intense radiation and stellar winds. Some of these stars are more than 100 times the mass of the Sun. They will not live long. In a few million years, they will explode. But in their short lifespans, they reshape their surroundings, dramatically compressing nearby gas, triggering new waves of star formation. Creation triggers creation. Violent seeds growth. The scale of energy released by a single massive star dwarfs anything humanity has ever produced. Yet those energies are routine in cosmic terms. Webb captures them in infrared glow heat radiating through dust clouds that would otherwise hide the action. And then, At even larger scales, Webb studies galaxy clusters, massive assemblies of hundreds or thousands of galaxies bound by gravity. These clusters contain not just galaxies, but vast halos of hot gas and dark matter. When Webb observes a cluster, it sees gravitational lensing arcs background galaxies magnified and distorted. By mapping those arcs precisely, astronomers can infer the distribution of dark matter within the cluster. Invisible mass becomes chartable, not seen directly but outlined by its gravitational influence. This is where observation becomes cartography. We are mapping the unseen architecture of the universe. And as Webb continues, patterns emerge. Galaxies cluster into filaments. Filaments connect into a cosmic web. Between the filaments lie enormous voids regions with relatively little matter. The universe on its largest scales resembles neural networks or sponge-like structures, threads of matter stretching across hundreds of millions of light years. Webb contributes high-resolution snapshots that fit into this larger map. From individual star systems to the cosmic web, the universe is hierarchical. Small structures nested within larger ones. Atoms within stars. Stars within galaxies. Galaxies within clusters. Clusters within filaments. Filaments within the expanding fabric of space-time. And somewhere within one modest spiral galaxy, on a rocky planet orbiting a stable star, observers piece together this hierarchy. We are not detached from it. We are a product of it. Webb's discoveries are not simply expanding our catalogue of objects. They are compressing our sense of separation. The same physics governing the first stars governs our sun. The same chemical evolution that enriched early galaxies made Earth possible. The same expansion that stretches distant light defines our cosmic horizon. There is no break in continuity, only scale. And Webb keeps stretching that scale outward deeper into time, further into structure, closer to the beginning. Not to prove how small we are, but to reveal how connected we have always been. And as Webb keeps looking, something subtle happens to our intuition. Distance stops feeling abstract. It becomes layered. Because when we look at a single deep field image, we are not just seeing far away, we are seeing multiple eras coexisting in one frame. A galaxy 5 billion light-years away appears beside one 12 billion light-years distant. To our eyes, they are neighbours, in reality. They are separated not only by space, but by billions of years of cosmic evolution. It is like looking at a forest where some trees are saplings and others are ancient redwoods, but instead of sharing soil, they share perspective. Webb collapses time into a single plane of sight. And once you realise that, the sky changes forever. Every point of light becomes a timestamp. Every faint smudge becomes an error. When Webb identifies a galaxy at extreme redshift Z values pushing beyond 10, we are looking at light emitted when the universe was perhaps 300 to 400 million years old. At that age, the cosmos had no mature spiral galaxies like the Milky Way. No stable planetary systems billions of years old. No long history of chemical recycling. It was an adolescent universe, intense, unstable, rapidly assembling itself. And yet, even in that youth, structure appears. This is where Webb's discoveries begin to press against expectation. In the earliest epochs, we expected to see small, irregular proto-galaxies building blocks that would later merge into larger systems. We do see many of those, but we also see surprisingly luminous systems objects that appear to contain significant stellar mass already. If confirmed, some of these galaxies formed stars at extraordinary rates. Hundreds of solar masses per year. For comparison, the Milky Way forms about 1 to 2 solar masses per year today. The early universe may have been a furnace of accelerated creation. Gravity pulling gas into dense halos of dark matter. Gas cooling rapidly. Stars igniting in bursts so intense they reshape their galaxies. It suggests that cosmic dawn was not a flicker. It was a blaze. And then there is reionization. After the cosmic microwave background was released, the universe entered a period sometimes called the Dark Ages. Neutral hydrogen filled space. There were no luminous stars yet to illuminate it. When the first stars formed, their ultraviolet radiation began ionizing that neutral hydrogen, stripping electrons away once more. This process transformed the intergalactic medium from opaque to transparent. It changed the universe's large-scale properties. Webb is observing galaxies that likely contributed to that transformation. By measuring the ionization state of gas around early galaxies, astronomers can estimate how rapidly reionization progressed. This is not a trivial detail. It is the difference between a universe that clears quickly and one that lingers in darkness. Webb is revealing that the first generations of galaxies may have been efficient at producing ionizing radiation. They may have punched holes in the cosmic fog earlier than expected. And the faster that happened, the sooner structure could grow freely. Again, the theme repeats. The early universe may have matured faster than we once thought. But Webb does not just rewrite timelines at the larger scales. It also reshapes our understanding of planetary systems closer to home. In our own solar system, Webb has turned its infrared gaze toward Jupiter, Saturn, Neptune, even asteroids and comets. On Jupiter, it reveals auroras glowing near the poles, charged particles interacting with the planet's magnetic field. On Neptune, it captures high-altitude methane clouds reflecting sunlight in delicate bands. On comets, it detects water vapor jets venting into space as ice sublimates near the sun. These are not distant mysteries. They are neighbours. And yet Webb sees them with clarity and depth that connects them to larger cosmic processes. Comets, for example, are relics, frozen leftovers from the early solar system. By analysing their composition, Webb helps reconstruct the conditions under which planets formed here. In that sense, Webb is not only looking outward into deep time, it is looking backward into our own origin story. Because our solar system formed from a molecular cloud enriched by earlier generations of stars. The heavy elements in Earth's crust came from supernovae long before the sun ignited. The water in our oceans may have been delivered by icy bodies formed in the outer solar system. Webb studies protoplanetary disks around young stars and finds water and organic molecules embedded in those systems. It suggests that the chemistry that seeded Earth is not unique. It may be a common byproduct of star formation, which tightens the tension around one profound question. If the ingredients are common, if planets are common, if water is common, what about life? Webb has not detected life, but it is beginning to narrow the field. It is analysing atmospheres of rocky exoplanets, measuring whether they retain air, searching for chemical combinations that would be difficult to explain without biological processes. This is slow, careful work, but it is real. For the first time, humanity possesses an instrument capable of analysing the atmospheric chemistry of Earth-sized planets around distant stars. Not by imagination, by measurement. And yet, even as Webb probes these intimate possibilities, it never loses sight of the largest canvas. Because the ultimate context for life is cosmology. The fact that we exist at all depends on the early universe behaving in very specific ways. If expansion had been slightly faster, matter might never have clumped into galaxies. If slightly slower, everything could have collapsed prematurely. If the balance of forces had shifted subtly, stars might not have fused heavy elements efficiently. Webb's observations refine our understanding of those balances. It is mapping how structure actually emerged, how quickly galaxies formed, how efficiently stars ignited, how rapidly chemistry diversified. It is replacing speculation with image after image after image, each one a timestamp, each one a reminder. We are not looking at a static painting of the cosmos. We are looking at a living archive. And with every deep field Webb releases, we peel back another layer of time closer to the first light, closer to the moment the universe transitioned from simplicity to structure, closer to the origin of everything we have ever known. And somewhere in all of this immensity, a quiet realization begins to settle in. The universe did not have to become this intricate. In its earliest moments, it was astonishingly simple energy expanding, particles forming, space stretching. The laws of physics were already in place, but complexity had not yet emerged. There were no galaxies, no stars, no atoms heavier than lithium. Just a hot, dense sea of potential. Webb is showing us how quickly that potential unfolded. Within a few 100 million years, the first stars ignited. Within 1 billion, galaxies were assembling with surprising speed. Within a few billion, large-scale structures, the cosmic web of filaments and clusters were well established. Complexity did not crawl forward reluctantly. It surged. And what Webb reveals most clearly is that this surge was not random chaos. It was structured emergence. Gravity amplified tiny density fluctuations differences so small they were once less than 1 part in 100,000. From those minute ripples, entire galaxy clusters formed. Think about that. Every galaxy, every star, every planet traces back to slight irregularities in the density of the early universe. Imperfections gave rise to structure. Without them, matter would have remained evenly distributed, no stars, no galaxies, no observers. Webb is, in a sense, mapping amplified imperfection, and it does so by reading light stretched across time. Each spectrum it records is more than a set of lines and peaks. It is a fossil record. When Webb measures the metallicity of a distant galaxy, the proportion of elements heavier than hydrogen and helium, it is estimating how many generations of stars have lived and died there. Low metallicity suggests youth. Higher metallicity suggests maturity. By comparing galaxies at different redshifts, astronomers can trace chemical evolution across billions of years. We can see enrichment happening. We can watch the periodic table filling in. In the earliest galaxies, heavy elements are scarce. A few 100 million years later, they are more abundant. A few billion years after that, planetary systems become more viable. It is a gradual layering of possibility. And then there is morphology, the shape of galaxies. In the nearby universe, we see elegant spirals and massive ellipticals. But Webb shows us that in the early universe, shapes were often irregular, clumpy, unsettled. Galaxies were colliding more frequently. Gas was abundant. Star formation was intense and chaotic. Order emerged over time. Spiral arms formed as disks stabilized. Elliptical galaxies formed from repeated mergers. The universe did not begin beautiful in the way we see it now. It became beautiful through interaction. Webb captures galaxies mid-transformation distorted arms, tidal streams stretching between merging systems, bursts of star formation ignited by gravitational compression. We are seeing evolution in motion. And then there are the smallest scales Webb can resolve in distant systems. Star clusters. Compact groups of stars born together in dense molecular clouds. In some nearby galaxies, Webb identifies clusters only a few million years old, hot, luminous, tightly packed. In older galaxies, it finds globular clusters, ancient spherical swarms of stars that formed early in galactic history and survived for billions of years. These clusters are time capsules. Some globular clusters in the Milky Way are nearly as old as the galaxy itself, over 12 billion years. They formed when the universe was still young. Webb's observations of similar clusters in other galaxies allow us to compare formation histories across cosmic time. We begin to see patterns. How star formation efficiency changes. How galaxy environments influence cluster survival. How chemical enrichment shapes stellar populations. This is not static observation. It is comparative archaeology on a cosmic scale. And the deeper Webb looks, the more it reveals that the universe has always been dynamic. Even now, galaxies continue to evolve. Stars are still forming. Black holes are still feeding. Supernovae are still exploding. But there is also a long-term arc. Star formation rates in the universe peaked about 10 billion years ago and have declined since. The cosmos was once more active, more luminous overall. We live in a quieter era. The great blaze of star formation has dimmed. Gas reserves are gradually being consumed or heated. Future epochs will likely see fewer new stars igniting. Webb helps chart this history. By observing galaxies at different distances and therefore different times, it reconstructs the rise and fall of cosmic star formation. It shows us that we exist in a middle-aged universe. Not in its infancy, not in its final twilight, but in a mature phase where structure is abundant, chemistry is rich, and visibility extends back nearly to the beginning. And this brings us back to something profoundly human. We are temporary. Our species has existed for only a fraction of a second in cosmic time. Recorded history spans mere thousands of years. Even the lifespan of our Sun, about 10 billion years total, is brief compared to the trillions of years some red dwarf stars will burn. Yet within this fleeting window, we built an instrument capable of seeing nearly to the beginning. Webb compresses cosmic history into something accessible. It does not make it small, it makes it visible. And visibility changes perspective. When you understand that the atoms in your body were forged in early generations of stars, when you see galaxies forming billions of years before Earth existed, when you realize that light older than the Sun is arriving tonight, your sense of scale shifts. You are not central, but you are connected, not significant in mass, but significant in awareness. Webb is a machine made of metal, glass, and gold. But what it truly extends is perception. It allows us to stand in the present and look almost all the way back to the origin of structure, to watch imperfection amplify into galaxies, to see chemistry accumulate into possibility, to witness the long unfolding that eventually produced us. And in doing so, it turns the night sky from a backdrop into a living archive of everything that led here. There is a point, when staring at a Webb deep field, where the mind resists. Too many galaxies, too much depth, too much time compressed into a single image. It becomes almost abstract. But then you remember something grounding. Every one of those galaxies is real. Not illustrations, not simulations. Each one is a gravitationally bound system of stars, gas, dust, dark matter structured across tens or hundreds of thousands of light years. Each one contains billions of suns, and in many of them, planets are almost certainly orbiting those suns. When Webb stares into a region that looks empty to the naked eye and reveals thousands of galaxies, it is not just increasing a count. It is multiplying possibility. And it forces a recalibration of rarity. For most of human history, we thought Earth might be the center of everything. Then we learned Earth orbits the Sun. Then that the Sun is one star among hundreds of billions in the Milky Way. Then that the Milky Way is one galaxy among billions. Now Webb suggests that even in the earliest epochs, galaxies were abundant. Structure was not rare, it was inevitable. Given the laws of physics, matter clumps. Given time, clumps ignite. Given fusion, elements diversify. Given chemistry, complexity accumulates. The universe appears predisposed toward structure, and that predisposition is visible in Webb's data. When it measures star formation rates in early galaxies, we see not hesitant beginnings, but vigorous activity. When it maps dust in distant systems, we see rapid recycling of stellar material. When it detects heavy elements in ancient light, we see the swift enrichment necessary for planets. The ingredients of worlds assembled quickly. But there is another layer to this. Webb is not just pushing deeper into space. It is pushing into the limits of detectability. There are galaxies so distant that even Webb struggles to resolve them clearly. Some appear as faint red smudges, barely distinguishable from noise until multiple observations confirm their presence. At extreme redshifts, light is stretched so dramatically that it moves beyond near-infrared into longer wavelengths. There will always be a boundary beyond which even Webb cannot see. But every time we approach that boundary, we learn something fundamental. For example, the distribution of galaxy brightness at early times, the luminosity function, tells us how common different types of galaxies were. If many bright galaxies exist earlier than expected, models must account for more efficient star formation. If faint galaxies dominate, they may collectively have driven reionization. Webb is measuring these distributions with precision. It is not just finding record-breaking objects. It is building statistical maps of early cosmic populations. And those maps feed directly into our understanding of how the universe transitioned from simplicity to complexity. Then there is something even more subtle. Webb's sensitivity allows it to detect faint background glow from intergalactic space. Not just discrete galaxies, but the diffuse light between them. This background encodes information about cumulative star formation over cosmic history. It is like measuring the ambient hum of billions of stellar furnaces combined. From that glow, we infer how much energy has been released across time, how much hydrogen has fused, how much matter has been converted into radiation. The universe has been steadily turning mass into light for nearly 14 billion years, and Webb is capturing the faint residue of that transformation. There is a thermodynamic poetry to it. Stars are engines of entropy increase. They convert low-entropy hydrogen into higher-entropy radiation and heavier elements. They radiate energy into space. Over vast timescales, stars will exhaust available fuel, star formation will decline, the universe will grow colder and darker. We are living in the bright era, an era when galaxies are still active, when heavy elements are abundant, when complex chemistry is possible. Webb shows us both the youth and maturity of this bright era. It sees galaxies in adolescence and others in seasoned adulthood. It sees stellar nurseries blazing with ultraviolet radiation. It sees older stellar populations glowing red with age. And by comparing these systems, we reconstruct not just what the universe looks like, but how it ages. This is cosmic demography, a census across time. And in that census, our Milky Way is not exceptional in size or brightness. It is a typical spiral galaxy. That typicality is profound. It suggests that the processes that shaped our galaxy mergers, star formation, chemical enrichment are common. If our galaxy is typical, and planets are common, and water is common, then the conditions that allowed life here may not be unique accidents. Webb does not confirm life elsewhere, but it tightens the statistical landscape. It shows that the universe is fertile, that chemistry unfolds naturally, that planets assemble as byproducts of star formation. And in doing so, it transforms the question from is it possible to how frequent? But even if life is rare, the fact remains, we exist in a universe capable of producing observers. Observers who can detect galaxies forming hundreds of millions of years after the Big Bang. Observers who can measure the chemical fingerprints of exoplanet atmospheres. Observers who can map dark matter through gravitational lensing. Webb amplifies that capability. It is an extension of curiosity, a precision instrument aimed at origins. And as it continues to collect data hour after hour, orbit after orbit, it is building an archive that will outlive the generation that launched it. Future astronomers will analyze Webb's datasets with improved models, refined techniques, new questions. Its observations will be revisited, reinterpreted, expanded. Because Webb is not just producing images, it is producing a foundation, a detailed, high-resolution record of the universe at multiple epochs, from local star-forming regions to galaxies at cosmic dawn, from planetary atmospheres to intergalactic structure. It is stitching together a coherent narrative of emergence. And in that narrative, one truth becomes unavoidable. The universe did not begin intricate. It became intricate. And we are witnesses to that becoming. Not because we were always here, but because, in this fleeting era of light and structure, we built something capable of looking back, almost all the way to the beginning. There is a moment, deep in the data, where numbers stop feeling like abstractions and start feeling like vertigo. Redshift 12, Redshift 13, light emitted when the universe was less than 400 million years old. At those distances, we are no longer observing galaxies that resemble our own. We are seeing protostructures compact, intensely star-forming systems still assembling their mass. And yet even proto feels misleading, because some of them already shine with startling brightness. To understand why that matters, imagine compressing the entire 13.8 billion year history of the universe into a single calendar year. The Big Bang occurs at midnight on January 1st. The first stars ignite sometime in mid-January. The Milky Way begins forming in March. Our Sun does not appear until early September. Dinosaurs emerge on December 25th. Humans arrive in the final minutes before midnight on December 31st. Webb is now imaging galaxies from mid-January. It is looking at cosmic infancy barely weeks into this metaphorical year. And those infant systems are not faint whispers of structure. Some are blazing. This is where scale turns almost violent. A galaxy forming 100 solar masses of stars per year in the early universe is converting gas into stars at a rate that would build the Milky Way's stellar population in a fraction of cosmic time. If such rates were sustained, galaxies could grow rapidly. But intense star formation also generates fierce radiation and stellar winds. Massive stars explode as supernovae within millions of years. Those explosions inject energy back into surrounding gas, sometimes halting further star formation. So early galaxies may have lived in cycles bursts of furious creation followed by temporary suppression. Webb's spectra begin to reveal those cycles. By measuring emission lines, hydrogen alpha, oxygen lines, ionized carbon astronomers estimate star formation rates, gas density, temperature. The fingerprints of physics are there, embedded in stretched light. And then there are the candidates that push even further. Objects whose redshift estimates place them within 200 to 300 million years of the Big Bang. At that age, the universe was only about 2% of its current age. If confirmed, these galaxies formed astonishingly early, which raises an almost destabilizing thought. How soon after the first atoms formed did structure ignite? Gravity had to work fast. Dark matter halos had to gather gas efficiently. Cooling processes had to allow collapse. Stars had to ignite, explode, enrich, and repeat. Webb's early results suggest that the timeline from simplicity to complexity may have been compressed. Not leisurely, rapid, and this speed matters. Because the earlier heavy elements appear, the earlier planets become possible. The earlier planets become possible, the earlier stable environments could, in principle, emerge. We do not know how soon life could arise. But Webb shows us that the raw materials were present surprisingly early. The universe did not delay chemistry for billions of years. It began layering it in almost immediately. And yet, even as Webb pushes toward the beginning, it also refines something closer to home, the measurement of cosmic expansion. By observing distant supernovae and calibrating them against nearby ones, astronomers measure how fast the universe is expanding today. That expansion rate influences age estimates, distance scales, and models of dark energy. For years, there has been tension between measurements derived from the early universe and those derived from nearby galaxies. The discrepancy is small, just a few kilometers per second per megaparsec, but significant enough to hint that something may be incomplete in our understanding. Webb's precision helps test whether this tension is due to measurement uncertainty or deeper physics. Perhaps dark energy behaves differently over time. Perhaps subtle systematic effects have skewed previous observations. Webb does not declare revolution. It sharpens resolution. And in sharpening, it narrows the space in which uncertainty can hide. But the deeper story is not in any single parameter. It is in continuity. From the cosmic microwave background to the first stars. From the first stars to early galaxies. from early galaxies to mature spirals, from spirals to planetary systems, from planetary systems to biology. Webb is stitching these phases together observationally, not as speculation, as data. When it detects carbon in a galaxy 13 billion light-years away, it is seeing the early chapters of the element that forms DNA. When it measures oxygen emission lines in a proto-galaxy, it is observing the element that fills our lungs. The atoms in your body were not created in isolation. They were forged in processes Webb now studies at cosmic dawn. There is a strange circularity to it. We are made of matter that emerged from early stars, and we have built a telescope to look back at those stars. The universe became conscious of its own origin. Not everywhere, not inevitably, but here, on this planet, in this narrow window of cosmic time, and Webb extends that consciousness outward. It does not just expand knowledge, it expands temporal reach. We can now trace a nearly unbroken chain from 380,000 years after the Big Bang to the present. The fog clears. Stars ignite. Galaxies assemble. Chemistry accumulates. Planets form. Life emerges. Observers arise. Observers build instruments. Instruments look back. The chain loops. And as Webb continues its survey probing deeper fields, analysing more exoplanet atmospheres, mapping more galaxy clusters, the picture grows denser, more precise, more intricate. The early universe was not empty. It was pregnant with structure. The present universe is not static. It is mid-transformation, and we are not detached. We are a later, luminous ripple in a story that began with fluctuations smaller than a fraction of a percent. Webb did not just look deeper than any telescope before it. It showed us that depth is not emptiness. It is ancestry. And the further back we see, the clearer that ancestry becomes. There is a threshold in human imagination that used to feel impenetrable. Before Webb, we had hints of cosmic dawn. We had models. We had indirect measurements. We had faint detections from Hubble, tiny red smears at the edge of visibility. But there was still a haze. Now the haze is thinning. Webb is not merely detecting the earliest galaxies. It is resolving them. Seeing internal structure, measuring their mass, estimating their star formation rates, identifying their chemical fingerprints. It is the difference between hearing that a city exists and walking its streets. And what we are finding in those early streets is motion. Some early galaxies appear compact and dense star factories compressed into regions only a few thousand light-years across. Others show extended shapes, hinting at disk formation beginning earlier than expected. In a universe only a few 100 million years old, gravity was already carving order from chaos. This challenges a comforting narrative that complexity requires vast stretches of time to emerge. Time matters, but the universe wasted very little of it. When hydrogen first began collapsing into stars, the feedback loops ignited quickly. Stars fused helium into carbon. Carbon and oxygen seeded future generations. Black holes formed in stellar cores and began feeding. Jets pierced interstellar space. Gas clouds were shocked, compressed, reheated. The early cosmos was not gentle. It was kinetic. Webb's observations of high redshift quasars, luminous objects powered by accreting supermassive black holes, add to this kinetic picture. Some quasars observed less than 1 billion years after the Big Bang host black holes with masses approaching 1 billion suns. 1 billion. To grow that massive in such a short time requires extraordinary feeding rates or massive initial seeds. This is not a small adjustment to models. It is a test of how quickly gravity can dominate. Perhaps the first black holes formed from direct collapse of enormous gas clouds. Perhaps early conditions allowed sustained near-maximal accretion. Webb is constraining these scenarios. It is mapping luminosities, spectral lines, and host galaxy properties. It is building a census of early black hole growth. And in doing so, it is revealing that the engines at the centres of galaxies were active almost from the beginning. Galaxies and black holes did not evolve separately. They co-evolved, which suggests that the architecture of the universe, its large-scale structure, was shaped by intertwined forces from very early on. But even as Webb stretches toward the beginning, it continues to refine the near. Take exoplanets again. In one system, Webb analysed the atmosphere of a hot Saturn-sized planet and detected sulfur dioxide, a molecule formed through photochemical reactions driven by stellar radiation. This is the first direct evidence of active atmospheric chemistry on an exoplanet. Not just passive composition, active transformation. Light from a star altering molecules in an alien sky. We are no longer simply cataloguing planets. We are studying their weather, their chemistry, their dynamics. In some rocky exoplanet systems, Webb is helping determine whether atmospheres exist at all. A planet without an atmosphere has exposed its surface sterilized by radiation, its heat escaping freely. A planet with a thick atmosphere can moderate extremes. Webb's infrared measurements during transits can reveal whether heat is redistributed across a planet's surface, indicating atmospheric circulation. These are subtle measurements, tiny variations in brightness. But from them, we infer climate. Across dozens or hundreds of light years, it is almost disorienting. We are detecting the thermal structure of worlds we cannot see directly. And this matters not just for curiosity, it matters for context. If Earth is one example of a rocky planet with a stable, life-supporting atmosphere, how common are similar configurations? Webb is beginning to move that question from philosophy into measurement. Not conclusively, but tangibly. And yet, no matter how intimate these planetary studies become, Webb never loses the backdrop of enormity. Because every exoplanet orbits a star, every star sits in a galaxy, every galaxy is part of the cosmic web, and that Webb stretches across billions of light years. When Webb observes massive galaxy clusters, it sees not just individual galaxies but the gravitational framework binding them. Dark matter halos extending far beyond visible stars, hot intra-cluster gas glowing in X-ray and infrared interactions, gravitational lensing arcs mapping invisible mass distributions. We are charting an architecture largely unseen. Ordinary matter, the atoms we know, make up only about 5% of the universe's total energy content. Dark matter accounts for roughly 27%. Dark energy driving accelerated expansion about 68%. Webb primarily observes the luminous 5%, but through lensing and structure formation, it informs our understanding of the other 95%. The visible traces the invisible, the luminous outlines the hidden, and as Webb refines our picture of early galaxy formation, it constrains how dark matter must have behaved. If structures formed earlier than expected, dark matter halos must have collapsed efficiently. If galaxies are more massive at early times, gas cooling and accretion processes must have been rapid. Every deep field, every spectrum tightens the allowable space of cosmic history. But beyond data and models, there is something more profound. Webb collapses existential distance. The light from early galaxies travelled billions of years to reach us. It crossed expanding space. It survived cosmic inflation, star formation cycles, galaxy mergers, intergalactic dust. It endured, and now it ends in a gold mirror floating in cold silence. Its journey concludes in human awareness. That fact alone reframes everything. We are not merely inhabitants of the universe. We are participants in its self-perception. The atoms that once drifted in primordial plasma now arrange themselves into neural networks contemplating their origin. Webb is a physical extension of that contemplation. It allows us to stand in the present and look almost all the way back to the first luminous structures, to watch the universe assembling itself in real time, delayed by billions of years of light travel. And as each new image arrives, each new spectrum resolves, The boundary between myth and measurement shrinks. We are no longer guessing about cosmic dawn. We are seeing its aftermath. Layer by layer, photon by photon. The darkness is not empty. It is ancestral. And Webb keeps reaching into it, pulling history forward into the light of now. At some point, the numbers stop expanding and start converging. Not converging toward smallness, but toward origin. Because the deeper Webb looks, the closer we approach a moment when the universe had no memory. Before stars and before galaxies, as before chemistry, there was only expansion and cooling. Webb cannot see the Big Bang itself. No telescope can. The earliest light available to us, the cosmic microwave background, comes from 380,000 years after that beginning. Before that, the universe was opaque plasma. But Webb walks right up to that curtain. It is mapping the era when the first structures pierced the dark. And here is what becomes almost overwhelming. The universe did not begin with galaxies waiting to happen. It began nearly uniform. Tiny fluctuations, quantum in origin, stretched across space by early inflation, became the seeds of everything. Fluctuations smaller than a whisper. And gravity amplified them relentlessly. Webb is now observing the amplified result. Every distant galaxy at redshift 10, 12, 13 is a fossil of those original fluctuations. Which means when we look at a deep field image, we are looking at the magnified aftermath of quantum ripples from the earliest moments of existence. Scale collapses. The smallest becomes the largest. And we stand in between. There is a strange elegance to that continuity. Quantum irregularities expand. Gravity sculpts them into halos. Gas collapses into stars. Stars forge elements. Elements assemble into planets. Planets host chemistry. Chemistry evolves awareness. Awareness builds telescopes. Telescopes look back at the ripples. The chain is not broken anywhere. Webb is helping us see that chain clearly for the first time. And it is not just looking at brightness and shape. It is measuring age gradients within galaxies. By analysing stellar populations, how blue or red they are, how strong certain spectral features appear, astronomers can estimate how long stars have been forming in a galaxy. In some early systems, there are hints that star formation began even earlier than the galaxy's observed epoch suggests, which implies that some galaxies may have started forming stars perhaps 200 million years after the Big Bang or even sooner. That pushes us close to the theoretical limits of how fast matter could assemble. The window between the cosmic microwave background and the first stars may have been shorter than once thought. This is not chaos. It is acceleration. And as Webb measures more galaxies at extreme distances, the statistical pattern becomes clearer. The early universe may have been more efficient at converting gas into stars than the modern universe. Gas densities were higher. Collisions more frequent. Dark matter hallus more compact. Everything was closer together. The cosmos was young and proximity breeds interaction. Interaction breeds structure. But the implications stretch forward too. If early galaxies formed quickly and enriched their environments rapidly, then planetary systems could, in principle, begin forming earlier as well. Rocky planets require heavy elements silicon, iron, oxygen. If those elements were already present within 1 billion years of the Big Bang, then the potential for terrestrial worlds existed astonishingly early. We do not know whether any such worlds hosted life, but the raw materials were there, which reframes our sense of rarity. Earth is not early in cosmic history. It formed about 9 billion years after the Big Bang. There may have been billions of years before Earth when planets with heavy elements already existed. We arrived late. Webb does not answer whether life arose elsewhere before us, but it reveals that the stage was set long ago. And then there is something even more humbling. The observable universe is only a portion of the total universe. Because light has had finite time to travel, we see only a sphere around us limited by cosmic age and expansion. Beyond that sphere, space almost certainly continues, perhaps infinitely. perhaps curved back on itself. We do not yet know. Webb refines the boundary of what we can see, but it also sharpens awareness of what lies beyond sight. Every time it extends the redshift record, we move the horizon of observation slightly outward. But the true boundary remains defined by time, and time continues. Light from even more distant regions is still on its way. In 1 billion years, observers, if any exist, will see slightly different horizons. In trillions of years, cosmic expansion will push most galaxies beyond detectability. We are living at a rare intersection, late enough that galaxies are abundant and structured, early enough that their ancient light is still arriving. Webb exists precisely in this intersection. It is a telescope for a vanishing opportunity, a chance to see cosmic dawn before expansion carries it permanently beyond reach. And that realization adds urgency to its images. Each deep field is not just discovery. It is preservation, a capture of photons that travel billions of years and will never return. Once absorbed, their journey ends. Their information is recorded, archived, studied. We become custodians of ancient light. There is something almost ceremonial about that. The universe produced photons during its first billion years. They travelled across expanding space for more than 13 billion years. And now they terminate in detectors cooled to near absolute zero. From there, they become data. From data, understanding. From understanding, narrative. We translate ancient radiation into meaning. And that meaning folds back into human culture, into classrooms, books, conversations, imagination. Webb did not just extend our vision. It extended our temporal identity. We are no longer creatures of the present alone. We are observers of deep time, witnesses to the first chapters of structure, participants in a story that began long before Earth and will continue long after the sun fades. And as the telescope keeps staring quietly, patiently, collecting photon after photon, the map grows richer. Closer to the beginning. Closer to the moment when the first stars broke the dark. Closer to understanding how a nearly uniform universe became a cathedral of galaxies. And in that understanding, something settles. We are not separate from cosmic history. We are its latest expression, looking back at its earliest light. And now we arrive at the edge of something almost unbearable to comprehend. Not the edge of space, not the edge of time, but the edge of visibility. Because there is a final stretch, Webb approaches a region where the first galaxies flicker into existence against the fading glow of the primordial universe. Beyond that, there are no stars yet, only darkness waiting to ignite. When Webb detects galaxies at redshifts greater than 12, we are seeing light emitted when the universe was less than 350 million years old. That number is easy to say, but compress it. 350 million years is less time than it took complex life to evolve on Earth after the dinosaurs disappeared. It is a blink in cosmic scale. And yet in that blink, the universe assembled galaxies. The first stellar engines roared to life. Black holes began their ascent towards supermassive dominance. Heavy elements started seeding interstellar space. The transformation from simplicity to structure happened almost immediately after conditions allowed it. This is what Webb is revealing. The universe did not hesitate. As soon as physics permitted complexity, complexity began. And here is where scale becomes deeply personal. Every atom in your body heavier than helium was forged inside a star. But those stars required previous generations to create the necessary elements. And those generations trace back to the first stars, the population 3 stars. We have not directly observed a pristine population 3 star yet. They were likely massive, hot, short-lived burning pure hydrogen and helium. They may have existed for only a few million years before exploding. But Webb is getting close to their era. By studying the earliest galaxies, astronomers search for signatures of extremely low metallicity indicators of stars formed before heavy elements were widespread. The moment we identify such a system clearly, we will be staring at a near-pristine chapter of cosmic history. We are circling the birthplace of chemical diversity. And while Webb pushes toward that beginning, it also sharpens something else, our awareness of fragility. Webb orbits at L2, a gravitational balance point roughly 1 million miles from Earth. It cannot be serviced easily. It carries a finite supply of fuel to maintain its orientation and orbit. Current estimates suggest it may operate for 20 years or more, thanks to efficient launch and fuel conservation. But not forever. There is an irony in that. A telescope designed to study billions of years of history has a lifespan measured in decades. A brief eye blink in cosmic time. And yet what it sees in those decades reshapes centuries of thought. Because Webb is not incremental. It is transformational. It is revealing that early galaxies may have formed faster. That supermassive black holes emerged earlier. That chemical enrichment began sooner. That planetary ingredients are common. That atmospheric chemistry can be detected across interstellar distances. It is tightening the cosmic narrative. But beyond discoveries, Webb has changed something more subtle. It has altered our psychological horizon. For most of human history, the night sky was mythic. Then it became mechanical. Then statistical. Now, through Webb's images, it becomes ancestral. When you look at a deep field, you're not just seeing distant objects. You are seeing the scaffolding of your existence. The galaxies that forged the elements. The stars that seeded chemistry. The processes that made planets possible. Webb compresses that realization into something visible. It transforms cosmology from abstraction into image. And those images carry emotional gravity. They are not empty black fields dotted with light. They are crowded with history, layered with epochs, dense with process. Every faint red smear in a Webb image represents a galaxy filled with suns. Every distorted arc represents light bent by gravity across billions of years. Every spectral line represents atoms absorbing or emitting energy long before Earth existed. We are watching the universe assemble itself, and in doing so, something quiet but profound emerges. The universe is not static. It is narrative. It begins nearly uniform. It develops irregularities. It amplifies them into structure. It enriches itself chemically. It stabilizes into galaxies. It forms planets. It gives rise to observers. And those observers build instruments that look back. Webb is not just documenting that narrative. It is participating in it. Because the act of observation changes the story not physically in the distant galaxies, but in our understanding. The cosmos is the same whether we look or not. But when we look, it becomes known. And knowledge alters the trajectory of a species. When we realized Earth was not the center, philosophy shifted. When we discovered other galaxies, a scale expanded. When we detected exoplanets, possibility multiplied. Webb has now shown us galaxies at the threshold of cosmic dawn in numbers and detail never before achieved. It has made the early universe visible, and visibility changes imagination. We can no longer imagine the beginning as abstract darkness. We see it studded with forming systems. We see starbursts igniting against blackness. We see the architecture of structure emerging, and we see ourselves reflected in that emergence. Because we are not late additions detached from origin. We are consequences of it. Webb has looked deeper into space than any telescope in human history. But what it truly revealed is this. Depth is not emptiness. It is memory, and that memory stretches almost all the way back to the moment light first began to travel freely. We are standing near the shoreline of time, watching ancient photons arrive like waves that have crossed a cosmic ocean. Each one carries a fragment of origin. Each one ends its journey in awareness. And as Webb continues to stare into the dark collecting, resolving, refining the boundary between beginning and now grows thinner, the universe is not silent in its infancy. It is luminous. And for the first time in history, We are watching that first light assemble the world that would one day watch it back. And when we finally step back after the redshifts, the spectra, the impossible distance is what remains is something quieter, but far more destabilizing. James Webb did not just look far. It looked early enough to change how we understand existence itself. For generations, the early universe was a blurred frontier, a mathematical boundary, a region defined more by equations than images. Now it has texture. Now it has shape. Now it has galaxies crowded, luminous, unexpectedly mature, glowing just a few 100 million years after the beginning. That alone rewrites the tempo of creation. The universe did not drift slowly into complexity. It surged. From near-uniform plasma to structured galaxies in a cosmic heartbeat. From hydrogen fog to star factories in less time than it took Earth to grow forests after extinction. And in those early furnaces, carbon formed, oxygen formed, iron formed. The elements that would one day circulate through blood and bone. Webb showed us that chemical ancestry began almost immediately. That enrichment was not a late refinement. It was an early inevitability. The first stars ignited, they exploded, they seeded space, new stars formed from enriched gas, planets assembled, chemistry layered. The chain never broke. And that chain leads directly here, to a species capable of intercepting photons that began their journey before our planet existed. There is something almost ceremonial in that exchange. A photon leaves a galaxy when the universe is young. It travels across expanding space for 13 billion years. It survives galaxy mergers, cosmic acceleration, the slow drift of clusters. And then it lands on a gold-coated mirror floating in cold silence 1 million miles from Earth. It is converted into data, into image, into understanding, into awe. Its journey ends in awareness. And awareness changes everything. Because once we have seen the early universe, we cannot return to imagining it as empty darkness. We know now that when the first light broke through the cosmic fog, structure followed almost immediately. We know galaxies assembled faster than many expected. We know supermassive black holes grew with startling speed. We know planetary ingredients were common. We know atmospheric chemistry can be measured across interstellar distances. We know the night sky is not sparse. It is dense beyond intuition. Webb did not make the universe bigger. It revealed how much bigger it always was. But more than scale, it revealed continuity. The same gravity shaping distant galaxies holds you to Earth. The same fusion powering early stars powers the sun warming your skin. The same chemical processes detected in far-off atmospheres shaped Earth's oceans. There is no divide between cosmic history and human history. Only distance. And Webb has collapsed much of that distance. It has given us images from a time when the universe was less than 3% of its current age. It has mapped galaxies assembling during cosmic dawn. It has traced chemical enrichment across billions of years. It has sampled alien skies. It has outlined invisible dark matter with gravitational arcs. It has refined expansion rates and pressed against the tension in cosmological models. It has walked us to the shoreline of the observable beginning. And it did all of this from a place of stillness. No roar, no spectacle, just patient accumulation of ancient light. There is a deeper realization beneath the discoveries. We are living in a privileged epoch, far enough from the beginning that galaxies exist, early enough that their earliest light is still reaching us, stable enough that life can emerge, advanced enough to build instruments. In trillions of years, the sky will be darker, galaxies beyond our local group will slip beyond detection, the cosmic microwave background will redshift further into obscurity. Future observers, if any exist, may never see what we see now. We are witnesses during a rare window of visibility. And Webb is our most powerful eye during that window. It has shown us that the universe did not begin as a grand cathedral. It began nearly featureless. And from microscopic fluctuations, it built everything. Everything. Stars, galaxies, planets, life, curiosity. The telescope floating in deep space is not separate from that process. It is the process turned inward. Matter becoming aware of its own origin. When we share Webb's images, when they spread across screens and classrooms and conversations, they recalibrate scale. They remind us that our conflicts, our timelines, our lifespans are brief within a 13.8 billion year arc. But they also remind us that brief does not mean insignificant. Because in this brief moment, we have achieved something extraordinary. We have seen almost to the beginning. We have intercepted light from cosmic dawn. We have confirmed that the darkness between stars is not empty, it is ancestral, layered, alive with history. And in doing so, we have anchored ourselves not at the centre of space, but within the centre of a story that began with quantum ripples, expanded into galaxies, forged the elements, assembled worlds, and produced observers capable of looking back. James Webb looked deeper into space than any telescope in human history. But what it truly revealed is this. The universe is not a distant spectacle. It is a continuum we belong to. We are late arrivals, yes, but we are also the first to see this far. And as long as Webb keeps its golden eye open in the cold silence beyond the moon, ancient light will continue to arrive, carrying the memory of the beginning and ending quietly in us.